Lesson 1.3, Solve Linear Equations. I think we mixed up the I can statements on this one. In this problem, we should say I can solve equations and I can solve verbal models. So we'll put expressions, we'll just make those equations, and then instead of create, because we did that in 1.2, we'll actually solve in 1.3. The definition for an equation is a statement where two or more expressions are equal. A linear equation can be written in the form ax plus b equals 0. To be linear, it's important to note that your variable only has an exponent of 1. It wouldn't be anything higher than that. A value is a solution of an equation if substituting the value for the variable results in a true statement. When asked to solve an equation, your goal is to isolate the variable on one side. Thinking about order of operations, we're going to apply PEMDAS, but in the reverse order. When you want to isolate a variable, move anything over that's being added or subtracted by doing the opposite. Then look at anything being multiplied or divided, and then last but not least, you would evaluate something with an exponent. But for linear equations, we shouldn't have that. The 4 examples on the right are just a variety of scenarios where we want to isolate our variable. In the first example, we have 4/5 x plus 8 is equal to 20. Key things to note when solving. We're going to keep our answers in fraction or integer form. We're not going to approximate with our calculator in decimal form. We're going to have to become familiar and comfortable in evaluating with these fractions. To get x by itself, I notice we have 4/5 being multiplied and 8 is being added. Thinking of order of operations backwards, we would actually get rid of the 8 first by moving it over using subtraction. That would leave us with 4/5 x is equal to 12. Since x is being multiplied by a fraction, we could divide, but we talked about in lesson 1.1 the idea of multiplying by the reciprocal. That would be equivalent to dividing by the fraction, and what multiplying by the reciprocal will do is allow us to multiply on the other side as well. So what I'm going to do is I'm going to write 12 as 12 over 1. And then we can just multiply straight across. On the left side, the 4 on top and bottom cancel, and the 5's cancel, giving you just x. On the right, 12 times 5 is 60, divided by 4, and that actually equals 15. Therefore, x equals 15. For the next example, on the right, notice we have a variable now on each side of the equation. 5m minus 2 is equal to negative m minus 2. In order to isolate the variable, we need to move them to the same side of the equation. I've got 5m on the left, which is positive, and negative 1m on the right. I'm going to move the negative 1m over simply by adding it. I'll also move the negative 2 then to the right by adding that as well. On the left-hand side, we end up with 5m plus m, which becomes 6m, and the 2's cancel. On the right, the m's cancel and also the 2's, leaving us with 0. All is not lost, however. To isolate our variable, getting m by itself, if we divide, division by 0 is pretty straightforward. If 0 is in the numerator, 0 divided by anything stays 0. And 0 is a valid solution for our variable. All right, let's try the 2 down below. I see lots of fractions and variables here. For example 3, we have 3/11 y plus 5 is equal to 4y plus 8. Taking a look at the two variables, if we want to get them on the same side, typically a good plan would be to move the smaller variable or the smaller coefficient over to where the bigger coefficient is. And in this case, that would happen by moving the 3/11 y over using subtraction. We can also move the 8 over to get the numbers on one side and the variables on the other. On the left, 5 minus 8 would give us negative 3. On the right, we've got to do a little bit of detective work to figure out our coefficient. I'm going to take that integer of 4 and write it as 4 over 1. Now, if we want to subtract 3/11ths, we would need a common denominator. Nicely, or at least in this problem, a common denominator between 1 and 11 would stay 11. All we need to do then is change that first fraction. If I want the denominator to be 11, I'm going to multiply that on the bottom and on the top. That's multiplying by the identity. And that will give us 44y over 11, which would be equivalent to the 4 we initially had. And now if we subtract 3/11ths, 44 minus 3 becomes 41. We should then have 41/11ths y on the right-hand side. Now to continue solving for y, since we're multiplying by a fraction, multiply by the reciprocal will cancel the fraction out. And if we do that on the left, we also need to do that on the right, we also need to do that on the left. So over on that right-hand side, the 11s cancel, the 41s cancel, giving us plain y, which is what we wanted. On the right, I'm going to put my integer of -3 over 1 and simply multiply straight across. 11 times -3 becomes -33. 41 times 1 is just 41. If you could reduce that fraction, you always want to reduce as far as possible, but in this case, 33 over 41 is simplified. Therefore, y equals -33 over 41. For the last example, we have two fractions, and notice both of the variables are in the numerator of those fractions. 2/3 d equals 3/5 d plus 4. In this case, let's go ahead and move the 3d over 5 over, and then the 4 will already be by itself. So we're trying to isolate that variable. As always, when we want to move things over, we'll do the opposite operation. And now we have to think about a common denominator of the 3 and the 5. Again, over to the right or wherever you have room, I'm just going to rewrite this 2d over 3 minus 3d over 5. Thinking about common denominators, what could both 3 and 5 go into? I think the smallest common denominator would be their product of 15. That means that first fraction, if we multiply the bottom by 5, we'll do the same on the top. And in the second fraction, we'll multiply top and bottom by 3. 5/5 times 2d over 3 would become 10d over 15. And then 3d times 3 would be 9d over 15. So now this becomes pretty manageable. If we have 10d minus 9d, that just becomes 1d over 15. That would be the left-hand side. On the right-hand side, the fraction cancels, and we have 4. So now if we have 1d divided by 15 equals 4, we can easily get rid of the 15 in the denominator by multiplying its reciprocal, 15 over 1. The 15s would cancel. Over on the right, 4 times 15 is 60, divided by 1 stays 60. And there's a variety of scenarios solving for a variable. When a variable is embedded in a parenthesis, we will apply the distributive property first to eliminate the parentheses, and then we'll try to follow the same steps as up above. In that first equation, we've got variables and parentheses on both sides. I recommend distributing any coefficients that are on the outside first to eliminate those parentheses. If we distribute the 3 in on the left, 3 times 5x becomes 15x. Minus 3 times 8 would be 24. On the right, be careful with the -2. We always have to just be mindful of those negatives. They kind of try to trick us. -2 times -x would become positive 2x. And -2 times positive 7 becomes -14. Distributing those coefficients in front into the parentheses now eliminates them. Make sure to drop down that 12x on that far right-hand side. So now to simplify, let's keep the 15x minus 24 on the left. On the right, we've got 2x minus 12x, and if we combine like terms there, that would give us -10x. With variables on each side, let's move one of the x's over. I'll take the negative 10x and I'll move it to the left by adding it. That means we'll take the negative 24 and move it to the right by adding as well. Combining like terms on that left-hand side, 15x plus 10x is 25x. The 24's cancel. On the right, the 10x's cancel. Negative 24 plus 24 would give us 10. Now this is pretty straightforward, I would think. To get x by itself, if we divide both sides by 25, x will equal 10 25ths, but 5 goes into both of those numbers. 5 will go into 10 2 times and into 25 5 times. That simplified fraction reduces down to 2/5. All right, I'm going to have you pause the video and try the example on the right. Distribute the 3 and 5 in and then combine variables on one side, everything else on the other. Once you feel you've solved the problem, press play and we'll see how you did. If you got x equals negative 7, that is correct. Distributing the 3 in on the left and the 5 in on the right gives us a variable on each side. No matter if you move the 3x or the 5x over and then the 6 or the 20 accordingly, you should still get negative 7 as your result. Our last example in the video has us creating a verbal model and solving for a particular part of the problem. During one shift, a waiter earns wages of $30 and gets an additional 15% in tips on each food bill. The waiter earns a total of $105. What was the total amount of the combined food bills? So if we think about the waiter's total earnings, their total wages come from two parts. They get an hourly wage, or they get like their earnings of $30, and then 15% on the total food bills that they get for that time that they work. So 15% would be in decimal form 0.15. And if we think about what that's of the combined food bills, so we'll call that X. X meaning the total food bills. That's what we're trying to solve for. Okay, so let's read this again. During one shift, a waiter earns wages of $30 and gets an additional 15% in tips on each food bill. The waiter earns $105. That means that is their total. We'll plug that in on the left-hand side. If I can get a color here, there we go. I kind of wanted to go with pink, 105. On the right-hand side, that $30 is standard. And then the waiter still gets tips from the food bills that were created from the time they were working. To figure out how much the food bills were, now we're going to solve for X. This just brings us to a linear function, or a linear model. To get X by itself, we'll move that 30 over. And I guess we didn't probably need the dollar symbol there, so you can delete that if you want. If I move 30 over on the left-hand side as well, 105 minus 30 would equal 75. On the right, that decimal 0.15 is being multiplied to X, so we'll divide. If we take 75 divided by 0.15, we would get a total of $500. And that is the amount of food bills during that waiter's shift on a particular night. And that's it for the lesson for 1.3. We'll finish the rest of the notes in class.